Okay, so we're going to be doing analysis of rolling motion. And I want to review a little bit of what we talked about yesterday and consider an object that is rolling along here with a speed of v and an angular speed of omega. The object that is rolling clearly has to have a circular cross-section. So we could be talking about a solid cylinder. We could be talking about a coupe that is a thin or hollow cylinder. Or we could be talking about a solid sphere or hollow sphere. And those are the objects that can roll. Now, when the object rolls, the key point about the motion is that the motion consists of translation plus rotation. Translation plus rotation. And this is the general rolling motion. If we have the idealized model of rolling without slipping, then we have the additional connection between the speed and the angular speed, which is that the speed of the center of mass is going to be equal to the radius times the angular speed. And the reason for that is very simple. And that is that if I look at a point on the outside, this point is going to undergo exactly one circumference of 2 pi r, right as the center of mass also undergoes a translation of 2 pi r. And you can see that because the object is rigid. So after one full rotation, then the object is going to be in the same position that it was before. So that point P, which clearly has traveled one circumference in order to get to this point, and the center of the circle have traveled the same distance. So we have rolling without slipping causes V equals R omega. Something else happens when you have rolling without slipping, and that is that we can identify the velocities of various points on the circle. If we have point P right here, if we have point Q right here, and we have point S right here, I'm not going to use R because we confuse it for radius, then the velocity of point P relative to the ground is going to be 0. And that happens because point P is simultaneously moving with speed negative v relative to the center, and it is moving, and then the center is moving at speed positive v relative to the ground, so that the whole thing adds up to 0. In other words, this point is rotating like so around the center, and its speed is r omega, and the direction is to the left. Meanwhile, the center relative to the ground is moving to the right at speed v, and so those cancel out. Whereas the velocity of point Q relative to the ground is going to be v in the I direction because of the translation, plus v in the j direction because of the rotation. And finally, the velocity of point S relative to the ground is going to be v in the I direction because of the translation, and v in the I direction again because of the rotation. So that the speed of a point at the top here is going to be twice the speed of the center of mass relative to the ground. So those are the kinematics of rolling without slipping. And now what we'd like to do is to take a look at energy considerations. Question? Okay. Why the velocity of p is equal to 0? Well, first of all, we remember that this was the familiar result that we've talked about a lot, and then p sticks and pushes off. Right? So that part doesn't surprise us. From a kinematic point of view, the reason that it is 0 is that the whole object is translating forward at a speed of v. Meanwhile, the various points on the wheel are rotating around with a speed of v, but in different directions. So at the bottom, the rotational motion is backwards with a speed of v. And so when you, if you take the velocity of p relative to the center, it is negative v in the other direction. And when you add that to the velocity of the center relative to ground, which is positive v in the other direction, you get 0. Better? Okay, now let's take a look at energy considerations. The total kinetic energy that an object will have while it is rolling is going to be the translational kinetic energy plus the rotational kinetic energy, or 1/2 mv squared plus 1/2 I omega squared. If we add the rolling without slipping condition, such that v is equal to r omega, then we can actually replace the omega with v over r, and get an expression for the kinetic energy purely in terms of the speed of the object. This is very, very useful. And in particular, if we take a look at some common objects, for example, if we take a look at a hoop, such that I is equal to mr squared for that hoop, then when I evaluate the expression for k total, I get 1/2 mv squared plus 1/2 of mr squared times v over r squared. And lo and behold, the radii cancel out with this expression. So that I get a contribution from the translation, which is always 1/2 mv squared, and then an additional contribution from the rotation, which for this shape is 1/2 mv squared as well. And it is 1/2 mv squared because every single point on the hoop is on the outside and is traveling with a speed of v relative to the center. So if we think about motion relative to the center is rotation, motion of the center is translation, then we have 1/2 mv squared for all those points rotating, and add to that the 1/2 mv squared for all those points additionally translating. So notice that a hoop that is rolling along with a speed of v has a kinetic energy that is greater than 1/2 mv squared because of the additional 1/2 I omega squared contribution, the additional rotation contribution. If, on the other hand, we have a solid cylinder, then the moment of inertia is going to be simply 1/2 mr squared. And because of that, when I substitute into the expression for k total, I get my translational component plus my rotational component, 1/2 I omega squared, and this gives me 1/2 mv squared plus now only 1/4 of mv squared. Why lower? Because many of the points, most of the points in my solid cylinder are distributed at radii that are less than r. They're distributed in towards the center, so their speeds are lower. They're going slower, and as such, they contribute less to the total kinetic energy. And the conclusion is that a solid cylinder with a speed of v has less kinetic energy than a hoop with a speed of v, because the points are distributed in towards the center. Does that make sense? Now, here's where this pays off. Let's consider this question. A solid marble of mass m, radius r, rolls down an inclined plane of height h. And angle theta. Find the speed of the marble. If A, it rolls without slipping. And just for comparison, let's compare that to B. It slides without rolling. And what circumstance would it have to be true in order for the object, for the marble to slide without rolling? What's that? No, it's a marble. But what sort of magical thing could I do to my inclined plane to make it so that the marble slides without rolling?
Grease it.
In other words, make it frictionless, right? So that would be the mu equals 0 case. All right, so we're going to analyze this in terms of energy, and then if we have time, we'll come back and we'll analyze it in terms of forces. Forces is definitely the slow way, but it gives us some additional insight in the analysis. And we consider initial and final states. In the initial state, the energy is purely potential. And we are justified in saying that the object is going to conserve energy because it is going to experience no non-conservative forces acting on it. It's going to experience it will experience a frictional force that will enable it to roll, but that frictional force is going to not take any energy away from it. It's simply going to take potential energy and convert that into rotational kinetic energy. So that the energy of the initial system is just mgh. there's no kinetic energy at the moment of release. And the energy at the final is going to be 1/2 mv squared plus 1/2 I omega squared. Now, what object should I model my solid marble as? What kind of sphere? Hollow or solid? Solid. Right. So, I'm going to use an I that is appropriate for that. And I'm going to replace omega with V over R because I'm rolling without slipping. Cancel here. The R squareds cancel also. So that what I get for my expression for final kinetic energy is 1/2 mv squared plus 1/5 of mv squared, or 7/10 of mv squared. We cancel on both sides, multiply both sides by 10/7, take a square root, then we get this guy right here. Now, if we contrast that with the sliding without rolling case, again we have conservation of energy, but now what changes is that my rotational kinetic energy is 0 because I'm not rolling. So that I get a really familiar result, V is equal to root 2GH. Now, let's compare these two numbers here. Which one's greater? Yeah, exactly. If the object slides without rolling, it will pick up greater speed. Why? Well, we can actually see it by going back and looking at how we solve this. In the case of sliding without rolling, we have no energy being distributed to rotation. If you think of MGH as a pool of energy, essentially, that is now distributed. In the case of rolling without slipping, we distribute that energy partly to translation and partly to rotation, and we do it in a 5-to-2 proportion. But when we slide without rolling, we distribute all of that energy into translation, hence our speed can be greater. So this now gives us some insight to answer some interesting questions. Suppose I take a hollow hoop and a solid cylinder, and I release them from the same height h on the same inclined plane, assuming that they roll without slipping. Which one will hit the ground first? Clearly the answer is the one with the greatest speed. And the one with the greatest speed is going to be the one that distributes the greatest amount of its energy into translation and the least amount of its energy into rotation. Which one will that be? A hollow hoop and a solid cylinder, same mass, same radius.
I don't remember the guys.
The solid cylinder, because more of its mass is distributed to the inside, and therefore it's going to consume less energy in rotation. It's going to put less energy into its rotation. It can rotate more efficiently than the hollow hoop. Speaking of knowing moments of inertia, probably a good idea to know the solid cylinder and the hollow hoop and to derive them for yourself once so that you can see why they work out the way they do. Pretty clear why the moment of inertia of the hoop is mr squared, because all of its points of mass are at a radius of r. So that's very straightforward. This guy is 1/2 mr squared, and you get that by integrating r squared dA. Since we have about 6 minutes left, I'd like to come back and analyze our marble question by taking a look at the forces. Actually, I'm going to clone our situation from here. Yeah. And paste. All right. So if we consider the forces that are acting on our solid sphere as it rolls down, those forces are going to be gravity pulling straight down, F1 pushing like so, and a frictional force that is going to be acting like so. And that frictional force is going to now cause rotation, about the center to get the whole thing rolling. And it is also going to retard the motion of the object so that its acceleration will be less than that of g. In fact, the acceleration will also be less than g sine theta, which is what we would expect in the slipping without rolling situation. Now, let's see that by doing a torque analysis about the center. If I do the sum of torques about the center C, then I can see that, no pun intended, there are going to be 3 forces acting. One of those forces is mg, it's pulling straight through the center, so its moment arm distance is 0. One of those forces is the normal force, but it is also pulling on a line through the center, and so its moment arm distance is 0. And the third and final force is going to be the frictional force, and its moment arm distance is going to be r, and it is going to be acting in a clockwise manner here, so we're going to give that a negative sign. And that sum of torques is equal to I times alpha. Since we're dealing with a solid sphere, our I is 2/5 mr squared, like so. What's that? And so we conclude, therefore, that, canceling one factor here, that the r times alpha is equal to the tangential acceleration, and therefore the acceleration is going to be equal to negative 5f over 2m. If we now take a look at the sum of forces acting on the object in the parallel direction, then the sum of forces acting in the parallel direction is going to be mg sine theta pulling down minus the frictional force pulling back up. And that is equal to m times a. see here? We had an expression for F. It was negative 2/5 ma. No, something's wrong. I double negativized myself. Here we go. That's the component there. So this should be equal to 7/5. And the acceleration here is therefore 5/7 of g sine theta. We can get the same result by simply doing a sum of torques about the point of rotation. Remember how we talked about that being a good idea? And so here, if we do a sum of torques about the point of rotation, then our alternate analysis looks like this. We call this point P. The sum of torques about point P is equal to mg times the sine of theta times r. And that's it. And the reason that it is sine of theta is that this angle right here is going to be theta, so that we have a simple torque calculation right there. And that is equal to IP times alpha. But IP is the moment of inertia of the solid cylinder about its point, about a point not through the center of mass. So we need to do a quick parallel axis computation and say that IP is equal to 2/5 of mr squared about the center of mass plus mr squared using the parallel axis theorem to shift it. And that's going to give us 7/5 of mr squared. Plugging into here, we get mg sine theta times r is equal to 7/5 mr squared alpha. Cancel a factor of r. Recognize that r alpha is equal to acceleration. I'll cancel a factor of m also. And find that the acceleration is 5/7 of g sine theta, which is what we discovered before. From the acceleration, we can then do equations of motion and get the same speed at the bottom. The conclusion is, therefore, that the analysis using forces gives us some insight as to the acceleration of our object, which is less than that of g sine theta, which explains why our speed at the bottom is less than we would expect if we were sliding.